Lastly, we have completed the topic determinant. Today we shall start one more unit which is about the mean value theorems of differential calculus. And in this unit, we shall study about the mean value theorems of a function, and that is, we are going to study the Rule's mean value theorem, Lagrange's mean value theorem, Cauchy's mean value theorem, Taylor's mean value theorem, and we are going to study about one more point is the Maclaurin's expansion of functions of one variable. And hence, firstly we shall study about these mean value theorems. While studying the mean value theorems, we have to consider one function which is the functions of one variable. Functions of one variable, and that function is defined in a interval. That function is defined in a interval. Then there are two types of interval. One is closed interval and another one is open interval. Firstly, we shall see what is meant by closed interval. Firstly, we shall see what is meant by closed interval. And hence, the closed interval is denoted by this notation. Denoted by this notation, which represents closed interval. Which represents closed interval of A and B, and totally whatever we have it, which represents closed interval of A and B, in which A is called starting point of the interval and B is called end point of the interval, and it totally represents the closed interval of A and B. Then what is meant by closed interval? What is meant by closed interval? Suppose that there is one point x belongs to the closed interval AB. X belongs to the closed interval AB. Then what is meant by it? And that is, x is any point between A and B. X is any point between A and B, and it is a closed interval. It means that x is equal to A as well as x is equal to B, and x takes any values between A and B, and that is x belongs to closed interval AB. It means that x is equal to A as well as x is equal to B, or x is equal to between A and B. That is, x takes the values between any values between A and B, as well as x is equal to A and x is equal to B. That is the meaning of closed interval. Then we have the second type of interval, which is called open interval. And the open interval is denoted by this notation. Which represents open interval of A and B. Then what is meant by open interval? Suppose that x belongs to open interval AB. X belongs to open interval AB. It means that x takes the values between A and B. X takes the values between A and B, but in this case x is not equal to A and x is not equal to B. That is, in case of closed interval x is equal to A, x is equal to B, but in case of open interval x is not equal to A and x is not equal to B, but x takes only the values between A and B. That is the meaning of open interval, and hence you remember what is mean by closed interval and what is mean by open interval. That is about the closed and open interval. Then, while studying the mean value theorems, always we have to consider one function which is the functions of one variable, and that function is always defined in a interval, and hence suppose that f of x is one function which is the functions of one variable x. F of x is a function which is the functions of one variable x, and it is defined in the interval AB. F of x is defined in the interval AB. Then what is mean by f of x is defined in the interval AB? It means that f of x exists in AB. F of x exists in AB. Then what is the meaning of exist? Exist means that function is always finite. Means that value is always finite. Exist means finite. Exist means finite, and does not exist means it is infinite. And here function is defined in the interval AB. It means that the function exists in that interval, or the function is finite. The function has a finite value in that interval. Here f of x is defined in the closed interval AB. Then f of x exists means that value exists. It means that value is finite. Then here we shall consider the value of a function f at a point A. The value of a function f of x at a point A. Then what is the value of a function f of x at a point A? And which is obtained by substituting x is equal to A in f of x. When we substitute x is equal to A in a function, it becomes f of A. And f of A is called value of f of x at a point A. Similarly here, the value of a function f of x at a point B. Substitute x is equal to B in a function. When substituting x is equal to B, it becomes f of B. Which is called value of a function f of x at x is equal to B. And hence f of A, f of B are called values of the function f of x at A and at B, which are obtained by substituting x is equal to A and x is equal to B in a given function. And hence to get the value of a function at any point, subput x is equal to that point in a function, you will get that value. Then f of a is the value, f of b is the value, and we say exist. We say exist. Exist means that the values are finite. The values are finite. Values are finite, and hence, while studying the mean value theorems of differential calculus for the functions of one variable, firstly you remember what is mean by closed interval, open interval, function is defined in the interval, then what is mean by f of a, f of b, and exist means finite values. Exist means finite, and does not exist means it is infinite. It is a infinite. Then we shall study about the first mean value theorem, and the first mean value theorem, which is called rules mean value theorem. Rules, R-O-L-L-E, rules mean value theorem. Rules mean value theorem, and we shall have it as a theorem, and the statement of the theorem is that state and prove rules mean value theorem. State and prove rules mean value theorem. For each mean value theorem, there is a statement, and hence firstly we shall see the statement of rules mean value theorem. Then in order to consider the statement of any mean value theorem, always you consider the function f of x, which is defined in a closed interval ab. To define or to consider the statement of a mean value theorem, always you consider one function f of x, which is defined in a closed interval a. And suppose that f of x is a function which is defined in an interval a. Then we have as next one is that function satisfies certain condition. That function satisfies certain condition. The first condition is about the continuity. The first condition, we have the function f of x, which is defined in the interval ab, and this function satisfies the certain condition. Out of that, the first condition is always about the continuity, and hence f of x is continuous in the closed interval ab. This is the first condition, f of x is continuous in a closed interval ab. Then second condition is about the differentiability of a function, and f of x is differentiable in the open interval. And hence each mean value theorem, that is function defined in the interval, and these two conditions are there always. These two conditions are there, and that is f of x is continuous, f of x is differentiable in the open interval. And in case of rules mean value theorem, we have third condition. And the third condition is that f of a is equal to f of b. F of a is equal to f of b. And hence, if any function f of x satisfies these three conditions, then according to the rules mean value theorem, there exists at least one point c belongs to open interval ab. C belongs to open interval AB. That is, C is any point between A and B, such that the value of f dash C, the value of f dash C is equal to 0, and it is the Rule's mean value theorem. There exists at least one point C belongs to the open interval such that the value of f dash C is equal to 0, which is the statement of Rule's mean value theorem. Then we have to prove this statement. It means that under all these given conditions, we have to prove this result. As f dash C is equal to 0. With the help of all these given conditions, we have to prove this result. Then we see what type of we have the proof of Rule's mean value theorem. Here, firstly given that f of x is defined in the interval AB. F of x is defined in the interval AB, and according to the given first condition, f of x is continuous in AB. F of x is continuous in AB. And according to the properties of continuity, we know that every continuous function is bounded. And hence, since f of x is continuous, and hence f of x is bounded in that interval, and f of x is bounded function. F of x is bounded means f of x has upper bound and lower bound. And suppose that capital M is upper bound and small m is lower bound of the function f of x in the interval AB. And hence, according to the first given condition f of x is continuous, and hence it is bounded, and hence capital M is upper bound and small m is lower bound. That is, LUB means least upper bound, GLB means greatest lower bound. Out of all the upper bounds, which is least, that is called LUB, and out of all the lower bounds, which is greater, is called GLB. And just you suppose here that capital M is upper bound, small m is lower bound of the function f of x in this interval. Then, to prove that result, f dash C is equal to 0, here there are two cases. Since capital M, small m are the bounds, then there are two possibilities. Both the bounds may be equal or both the bounds may not equal. And hence, first we shall consider both bounds are equal. Capital M is equal to small m. Capital M is equal to small m as case 1. Now here it is given that f of A is equal to f of B. F of A is equal to f of B. And f of A and f of B are the values of a function f of x in the interval AB. It means that f of A and f of B are the bounds. May be upper and lower bounds, and both bounds are equal. Which are equal to these two bounds, capital M and small m. Means all these bounds are equal. And when all the bounds are equal, then that is equal to the function f of x. That is equal to the function f of x according to the property. And here upper bound is equal to the lower bound, which are equal to the bounds of the function in that interval. It means that it equal to the function f of x. If so, f of a is equal to f of b is equal to capital F is equal to small f is equal to f of x. Means this function f of x is equal to capital M or smaller m, where these bounds are nothing but constant. Means f of x is reducible to a constant, that is it is equal to constant, that is f of x is equal to constant. F of x is equal to capital M, small m, which are constant quantities. Means f of x is constant, and it is holds good for all values of x belongs to AB. All values of x belongs to AB. Now f of x is equal to constant, and we want f dash. We want f dash, that is the derivative of f of x, and hence you take the derivative both sides. Derivative of f of x is denoted by f dash x. Derivative is denoted by f dash x, and derivative of constant is 0. Constant is 0. That is f dash x is equal to 0, which is true for all values of x belongs to AB. Belongs to AB. But we have to get it is f dash c, where c is any point in AB. And when we consider c is any point in AB, then we shall consider the value of f dash at the point C. Means replace x is equal to c. By substituting x is equal to c, it becomes f dash c is equal to 0. F dash c is equal to 0, and hence when these two bounds are equal, then that result holds good. That result holds good. That is the proof in one case. Now we shall consider the second case. Second case, here you consider the bounds are not equal. Bounds are not equal. But it is given that f of a is equal to f of b. According to the given third condition, f of a is equal to f of b, and now we have supposed that capital M is not equal to small m. Then by considering these two results, that is f of a, f of b, going to be upper bound and lower bound, and these are not now equal. These are not now equal. Then according to these two results, out of these m and one is different from f of a and f of b. Means out of capital M and small m, the one value f of a or f of b, the one value is different than f of a and f of b. That is the meaning when we consider these two results together. Now suppose that out of these two values f of a and f of b, capital M is not equal. Capital M is not equal. That is, we have supposed that. Now again, f of x is continuous according to the first condition. If f of x is continuous, then it attains the bounds at least once in AB. If the function is continuous, then the function is bounded, means there is upper bound and lower bound, means the function attempts its bound at least once in AB. And suppose that C is any point C is any point belongs to AB, then f of C is going to be the bound. The value of a function at the point C is going to be the bound, and that bound we are going to consider upper bound, and that is f of C is upper bound. F of C is upper bound. Upper bound. If f of C is upper bound, then according to the definition of upper bound, f of C is maximum value. F of C is a maximum value, and hence f of C is maximum because we suppose that it is the upper bound. Now f of C is maximum value, then according to the definition of maximum and minimum value, here f of C is greater than or equal to f of C plus h, means f of C is the value at C and f of C plus h is the value at C plus h. Then here f of C is maximum value, means this f of C is greater than any another value, that is f of C plus h, and also f of C is greater than f of C minus h. C plus h is and C minus h, which are the neighborhood of the point C, and f of C is maximum. Then according to the definition of maximum value, this value is always greater than any another value, means this holds good according to the definition of maximum value. Then we have this inequality, we shall simplify as transfer f of C to this side, then f of C plus h to this side minus f of C plus h. 0 is greater than, change the sides. When you change the sides, this equality sign changes is less than or equal to 0. Similarly here, you transfer this term to this side, f of C minus f of C minus h, which is greater than or equal to 0. Here, by transferring directly it to this side, it remains greater than or equal to 0. But here, we have transferred it to this side, and then we changed the sides, and when the sides change, the inequality sign changes, greater become less than, and it is true when h is positive, it is true when h is a negative. Then we have to find the value of f dash, and according to the definition of a derivative, we know the definition of derivative as limit as h tends to 0 of f of x plus h minus f of x divided by h, and hence to get that expression which is in the definition of derivative, here to this expression divided by h to this expression divided by h, and when divided on this side it remains 0, and according to the definition we have to take the limit as h tends to 0, and hence limit of it as h tends to 0, which is nothing but f dash c, and this limit also going to be f dash c, and hence the limit of these two expressions as h tends to 0, as h tends to 0, according to the definition of a derivative, this is going to be the derivative of f of c, that is f dash c, which is less than 0 for this expression, and for this expression which is greater than 0. Now here we have the two results simultaneously. F dash c is less than 0 and f dash c is greater than 0. And these two results simultaneously holds good only when that quantity is equal to 0. Means f dash c must be equal to 0 where c belongs to AB. C belongs to A. This is that is divided by h to get the expression contained in the definition of a derivative and taking the limit, and according to the definition of a derivative the limit is f dash c and limit is f dash c, and here once it is less than and once it is greater than means that quantity must be equal to 0, and hence it is the proof of rules mean value theorem. You go through it and check that what type of steps involved in the proof, and hence you remember closed interval, open interval function is defined. What is mean by f of a value exists means that is finite, and in mean value theorem always these three are there. Function is defined, function is continuous, function is differentiable, continuity in closed interval, differentiability in open interval. These are there in case while considering the statement of any mean value theorem. Next time we shall see next. Tùy